Hello, everyone, and welcome back to another episode of The Bryce is Right. And tonight we are discussing cosmology, the universe, space, time, gravity, the Big Bang Theory, not the TV show. We're going to be discussing it with an astrophysicist. So I'm very excited about tonight's episode. And it's not just any astrophysicist, it is none other than Dr. Ethan Siegel. Ethan is a science writer for Forbes magazine, as well as a content creator for the podcast Starts with a Bang. He's also a recurring contributor to Promethean Secular Frontier, which is how I know him. And he does great stuff over there. And I thought that I would invite him to come on my show and educate my audience on science and the universe and all of that good stuff. So, Ethan Siegel, come on down. You are the next guest on The Bryce is Right. How you doing?
This is like going to make my 6-year-old dreams come true when I was like dreaming that someday Rod Roddy would call my name, but it's Bryce Cornell instead.
There
I
you
will
go.
come on down. Welcome. Welcome to me. Yeah. Thanks for having me. I think that the story of what we know and how we know it, this picture of the universe, this is something that I think should be a story that everyone who's curious about it, this story should be available to them. So if you've got any questions that are like deep or hard or complicated and you're like, oh, I didn't think I'd be able to understand that, ask, because I want you to understand it, and I think you can.
Well, you see what I mean? Pick the right guy. I picked the right astrophysicist to be able to talk to a lay audience, which is what my audience is. So I mentioned at the top of the show, we're going to be talking about cosmology. And I think that that's a term that is used a lot in kind of the circles that I run with online, but I'm not sure if it's fully understood. So the first question, very basic, I just want to make it pretty clear about what we're talking about. What is cosmology, and what's the difference between cosmology and astronomy?
So first off, I'm pretty happy that you asked me what's the difference between cosmology and astronomy, and not what's the difference between cosmology and cosmetology. Because the difference between cosmology and cosmetology is Planck's constant, not Mach's factor. But the difference between cosmology and astronomy is that astronomy is when we look out at the universe, what do we see? What do we see out there, and what's it all about? What's it made of? What can we learn is going on from looking at it? When we talk about cosmology, we're asking a very specific aspect of astronomy. We're basically saying, okay, when we look out at the universe, what is the whole thing doing? What is it made of? How did it get to be the way it is? How was it born? And what is its fate? We're asking big questions about the cosmos as a whole when it comes to cosmology. So astronomy is a part of cosmology because it informs, from the observational side, it informs us about, okay, what do we see when we look out at the universe? But we also have this whole theoretical side based in physics where we say, okay, here are the laws of physics, let's apply them to the universe, and then let's put that whole picture together between the laws of physics we know and the astronomical stuff we observe, which falls into observational cosmology. Can we synthesize all of this together, and what kind of picture do we put together? And we can do this about tiny, tiny aspects like individual particles or subatomic processes that happen. And we can do this on the largest cosmic scales, galaxies, galaxy clusters, the cosmic web, or even the universe as a whole.
So it sounds like cosmology is really much broader, that astronomy is more of a subset of cosmology, whereas you're astronomy, you're just looking, you're studying the universe through what you see, but in cosmology you're actually making predictions about where things came from, what their end is, and all of that.
That's one way of looking at it. I actually look at it as cosmology is a subset of astronomy. Like I look at astronomy as astronomy is really broad, because astronomy if you are building an instrument, you're an astronomer. If you are analyzing data that someone else took, you're an astronomer. If you're making theoretical predictions about what happens in astrophysical environment, you're an astronomer. And if you're the one looking through the telescope or making your computerized stuff look through a telescope, you're also an astronomer. A cosmologist is really concerned with answering specific large-scale questions about the universe. So for me, I would say, a subset of astronomer is astrophysicist, and a subset of astrophysicist is cosmologist. And to me, if you want to say like, well, cosmology, that's the best one. I mean, sure, I'll take that. That's why I went into it, because for me, it was the best one. But for other people, other aspects of astronomy that have very little to do with cosmology, like individual stars or individual galaxy clusters or gas or dust. Other people are interested in those things. Those are just as worthwhile pursuits as cosmology is, even though most of their applications aren't cosmological in nature.
I'm an astronomer. I like it. You talked about why you got into it, and that's kind of where I wanted to go next. How did you get into this? Where did the interest come from, and at what age did you become interested in science? When did you know you wanted to do this?
Those are not questions that have the same answer. Like, I was interested in science when I was young. I was interested in lots of things. I remember when I was a kid getting a microscope and being amazed that I could look at these things on these little slides and actually see this whole universe of things that was happening below what my eyes could see. But if you magnified it enough, you could see it. I remember waiting for the day where my dad would cut himself shaving so I could get some blood for a slide to try and see the red and white blood cells.
Wow.
But I also remember I grew up in New York, and I got a telescope. And I had no idea how to use this telescope. So I'm like 6 years old with a cheap, crappy telescope in New York.
Mm-hmm.
So what do? I'm like, oh, I know. I'll wait till the moon is full, and then I'll go look at the full moon. Pro tip, don't look at the full moon as your introduction to looking through a telescope. What a waste. You should always, if you're going to observe the moon, the best place to observe the moon is what we call the terminator, the difference between night and day on the moon, because that's where you see the most what we call relief. That's where you see the craters on the moon, the shadows on the crater walls, the stark difference between night and day. If you're going to look at the moon, that's the best way to do it with a telescope, is look at the edge between night and day. If you look at a full moon, it's day everywhere on the moon, so you're blowing it. But for me, I had sort of a monumental moment. Like, I'd always been interested in math and science, and school was a good time for me for most of my childhood. But I remember being like 11 years old, and we went upstate. And upstate...
You're from the Bronx, right?
I was born in the Bronx. It's where I went to high school. I also spent a lot of time in Yonkers, New York, which we will often call the Lost Borough, which is just north of the Bronx.
I'm from Brooklyn and Queens, so I kind of Wikipedia stalked you and realized that you were from the same city.
Oh, so, yeah, we are. I went to Bronx Science, if you're familiar with that high school. Yeah,
I am. I didn't get in.
Oh, no, I didn't. I'm gatekeeping. Boo.
So I imagine.
Anyway, I'm 11 years old. I'm upstate, and I look up, and I couldn't see the Milky Way or anything, but for me, being able to see like hundreds of stars was revolutionary. And I remember laying out on this grassy field, and all of a sudden, I grabbed the grass as I'm laying on my back. I grabbed the grass with my fingers really hard because it was so disorienting to have this huge canopy of stars above me for the first time that I actually felt like I was going to fall up into the space that I was looking into. And it was actually a little frightening and a little disorienting. And then I sort of realized, like, whoa, like there's something that I can't explain that's kind of calling me about this. And as I learned more about mathematics, I started to ask these weird questions like, hey, you know how if you're on the surface of the earth and you go far enough in one direction, you'll loop around the circumference of the Earth and come back to where you started? What if
Ethan,
space is the same way?
Are you trying to tell me that the Earth is not flat?
Well, we can get into
flat.
that if that's what you want.
No, I don't.
If that's where you want to go, we can get into that.
Absolutely not.
I did write a piece a few years ago addressed to Shaquille O'Neal about how you can prove the Earth is flat. Just kidding. How you can prove it's not flat. Because he famously came out as a flat. You know. Okay, we're going to get into some weeds. So I'll say I don't think he was. I think that was him joking around. I think when Steph Curry said something about it, I think he was joking around. I think a lot of people who say these things say it for the same reason that a lot of people when we were very young were like embarrassed somehow if they got an A in school. Mm-hmm. Like you would want to hide that because you might get bullied for it, or people might think you were a nerd, or people might like somehow we've decided that being a high achiever is something to be ashamed of, and that being mediocre or even below mediocre is something that makes you cool. I don't know how to frame it other than to say like, look, on the one hand, you can have actual knowledge, and on the other hand, you can have glorified ignorance, where you're like, I'm too cool to know this. I'm too cool to get this right. And, that's just not how we do things. When I'm asking a question, I don't just want to know an answer. I want to know the right answer, and I want to know how we know that's the right answer. And if you can be curious that far into something at that level to say, I want to know what we know and I want to understand how we know it, you would be surprised at how far that gets you. And also how far that gets you just asking those questions into uncovering like, oh, like I thought this was a well-reasoned thing. And as you're telling me what we know and how we know it, I realize you are talking nonsense. You have no idea what you're talking about, because people who have positions that can be destroyed with reason or logic or evidence or facts. Like, I'm not interested in what doesn't survive that scrutiny. If you are going to scientifically scrutinize something and you're going to ask, what is true and how do we know? If your arguments can't hold up to that, then you don't really have a very good argument for why things are that way.
You know, your story about going up to upstate and looking at the stars really kind of struck a chord with me, because I remember, as I said, I'm from New York too, and I know that just the amount of light pollution in the city, your experience of what space looks like is very different from people who grow up in rural areas. And I remember my first trip down to, I had family that lived in rural Georgia, away from the city, and the nights there, I was blown away. I had a very similar experience as the one that you described at about the same age. And it was, I didn't go into the field, obviously, but it definitely got me interested in space. And I'm a huge science fiction fan. And so that's when I started watching Star Trek and all of these things. And I was just curious, are you a science fiction fan? And if so, what would be your favorite things?
Well, I did write a book on Star Trek, so if I'd be remiss if I didn't say that I'm a big fan of Star Trek. So the book I wrote is called Treknology. When I was in high school,
I know this book. I haven't read it, but I didn't know that you wrote that. I'm definitely getting it now.
It looks like this.
Yep. All right. Wow. You learn something new every day.
Yeah. So when I was in high school, The Next Generation was airing. I think it came to an end in maybe my junior year of high school. And then my senior year, this book came out, and it was called The Physics of Star Trek, and it was written by Lawrence Krauss. And I read this book. And I was like, oh, this is pretty interesting. He focuses on some of the physics aspects, and he works quantum physics and cosmology into it. And in that subsequent time, from the mid 90s until now, I went to college, I went to grad school, I became a cosmologist in the same subfield as Krauss. And so when I realized we're getting on to the 50th anniversary of the original series and we're getting on the 30th anniversary of the debut of the Next Generation, wouldn't it be fun to look not just at the physics-based technologies, but all of the technologies from Star Trek, or as many as I could fit, and say, okay, it's been 50 years since the original, 30 years since Next Gen. What are we looking at? How close are we to having these technologies actually be a reality? How many of them are still impossible? How many of them that we once thought are impossible are now possible? How many of them are we already well on our way to? How many of them have we surpassed Star Trek's dream for what they would be? So we took a look at 28 different technologies, from replicators to, your pads, your personal assistant digital display or whatever it is, which, as you pointed out, a smartphone goes well beyond the dreams of any Star Trek device.
Right.
I think Lieutenant Uhura in the original series had an
Bluetooth
electronic clipboard, which was like, oh, you could write on this and it'll actually save what you write electronically, like one of those flip and sketch things that if it had a save button.
She had the Bluetooth earpiece as well.
She did. She had the wireless headset. They had the big walkie-talkie universal translators.
So that's Star Trek. I'm glad you're a fan, and I'm definitely checking out that book. The other medium, most people know that I'm a huge fan. I'm wearing a Superman shirt, so it wouldn't be now that I have a scientist on board, I figured I would ask you a question about that. And basically, if you had to guess, how does Superman fly?
Well, we all know, if you're a fan of Superman, that Superman gets his powers from the yellow sun.
That's right.
Over on Krypton, where he's got a red sun, he has no powers.
Yeah.
Right? He's just a normal baby super guy. Like, he's just Jor-El's kid, right? He's Kal-El, the kid of Jor-El. Nothing super famous, but you get him a yellow sun. And what happens? Well, all of a sudden, he's super powered. So if I had to say, what is it about a yellow sun that's different than a red sun that allows Superman to be so powerful, I would have to say, well, look, a yellow sun, everything, if you heat it up, it's going to emit what we call a black body spectrum of radiation. This is why lava is red, right? It's because it's just rock. It's just rock, but you heat it up hot enough and it's going to start radiating heat, right? Hot things don't look hot. You touch something on the stove and you go, oh crap, I burned myself. Why? Well, because it's just a piece of iron and it's not hot enough to glow. So you touch it, you burn yourself because it's emitting infrared radiation. Well, you turn up the heat even more, it'll start emitting visible radiation. You turn the heat up even more, and you'll start getting ultraviolet and X-ray radiation. So our sun, we get quite a bit of ultraviolet radiation. A red sun, not so much. So I would say that's probably what it is. Whatever it is that's giving Superman his powers, it's got to be coming from the sun. So I'm going to say that Superman must have some internal either battery or capacitive cells that they can absorb this high energy radiation and emit it later on in a burst. And when he does, I guess he can make himself thrust like that, or he can figure out some way to manipulate Earth's magnetic field, although I've also seen him fly in space. So presumably he can emit his own thrust. So I would say whatever mechanism is, Superman is solar powered, and not by every sun, only by suns that are at least of a certain temperature.
That's the first scientific answer I've ever gotten to that question. So that was more than what I expected, but I appreciate it because, as I said, no one is a bigger fan than I. That I know.
Well, that's great. That's great. I love Superman. Superman, to me, he's always the hero that if you gave a good person power, how would they use it? And that is so antithetical in so many ways to our world, where the people who seek power are the people who absolutely should not have it.
Right. Yeah. So on to the good stuff, or the meat of the show, so to speak. You are a cosmologist. You've talked a lot about the Big Bang Theory, not the TV show, but the actual theory of how the universe came to exist in the state that it does. So if you had to describe the Big Bang Theory at the ninth grade level to the best of your ability, how would you describe it? There are doubters of science, and these stories that these scientists tell about where the universe came from. But how would you explain it to someone who doesn't understand?
So you have to realize in the universe, when anything happens, you can either say, okay, a thing is happening. What is happening to try and either resist it or to try and keep it going? So I'm going to tell you that the universe, when we look out at it, we see all the different stars out there, all the different galaxies out there, as far as we can look with like the Hubble Space Telescope or any telescope. As far as we can look, there are stars and galaxies going back tens of billions of light years, right? Long time in the past. So when I say, what is the Big Bang? I first have to recognize an observation that came before the Big Bang, which is that this is a little bit puzzling. When you look at a galaxy, you're not going to see the exact same light that you see from the stars within our galaxy. We know that atoms are the same everywhere in the universe. A proton is the same, an electron is the same. The laws of physics, as far as we can tell, are the same. So if I have electrons orbiting on an atom, and the electrons cascade down the energy levels, they're going to emit light. They're going to emit light of a specific wavelength, right? A wavelength is what defines light. Well, here's an interesting thing. When we look out at galaxies, the closest galaxies to us, their atoms look like they're doing the same thing our atoms are doing. But when we look farther and farther and farther away, if I said, okay, hydrogen emits this line and this line and this line. It has these whole series of lines. When I look at a nearby galaxy, I see very similar lines to what I see on Earth. When I look farther away, I see these lines are actually shifted to
Is that red
wavelengths.
shifting?
It is red shifting. We say red because redder light is longer wavelength and bluer light is shorter wavelength. So we say red shift because these lights get shifted to longer wavelengths. The farther away a galaxy is, the more its light is red shifted. So why? Why is that happening? Well, the thing we realized back in the 1920s and 30s is that this is because Einstein's equations actually predicts that the universe is going to expand. If I take a universe and I fill it with matter evenly, and I say, don't expand, what's going to happen? The whole universe will collapse fast. It will just collapse into a black hole, boom, singularity, game over. That didn't happen. And that isn't happening now. So instead, you say, okay, well, look, what is happening if I take this universe and I fill it with matter and I say, hey, physics, right? Astrophysics, cosmology, come on, do your math. What's going to happen? I actually get two solutions. Just like if I said, hey, Bryce, what's the square root of 4? You would tell me 2, and I would go, are you sure? And you'd go, oh, crap, he's trying to trick me. And you're correct, because it could be 2 or it could be -2. Right? 2 squared is 4, but -2 squared is also 4. When we put those equations in and we solve them, we find that, the universe could be expanding or it could be contracting. The equations don't tell us. You have to actually look at the universe and see what's it doing in order to know. And so we see this and say, oh, it is expanding. So this expanding universe is where the idea of the Big Bang came from, to say, okay, look, we see all these objects out there, galaxies, and the farther away they are, the more the light is redshifted. So that means the universe is expanding today. Well, if it's expanding today, that means in the future, it'll be bigger and less dense. And that also means earlier it was smaller and more dense. So the universe began from a hot, dense state and expanded and cooled to become the way it is today. The Big Bang is the earliest moments that we can describe the universe as hot, dense, full of matter, and expanding. So I would say, if you ask me what's a simple version, now that we've had all this, 5 minutes of background, how would you describe the Big Bang? I would say the universe is a race. It's a race between the expansion of the universe, whatever this initial expansion was, which works to push everything apart, and gravity, which works to pull everything back in. It's this attractive force that works to pull everything back together and slow the expansion rate down. So the universe is a race between expansion and gravitation, and the Big Bang is the starting gun of that race.
And if I were to ask you to elaborate a little bit at the slightly higher than ninth grade level, I'm sure a lot of people would be curious about why that's happening. And my basic understanding is it has to do with the things in the universe that we don't exactly see, but we know has some sort of an effect. So we hear about these terms like dark matter and dark energy and inflation, and they all seem to be related to this idea of the expanding universe. So what are they?
Sure. Let's just take on the big three all at once. So, okay, if I said, okay, look, so you're a smart guy. You said, okay, we're going to start off with this hot, dense, expanding thing, and we're going to let it expand and cool and get less dense, and then it'll gravitate and form stars and galaxies and blah, blah, blah. And here we are 13.8 billion years later. Fun story, right? Well, here's the thing. If I start off in the early universe and I say, hey, guess what? If my universe is full of stuff and it's really hot, won't all these atomic particles, subatomic particles, won't they all try to fuse together when things are very hot and dense like they do in the center of the sun and all stars? Won't they try to make heavy elements and fuse together and have these runaway reactions? And the answer is the universe would love to do that. But it has to wait. It takes time. So let's say we're trying to grow the stuff in the universe. If I said, I've got this sea of particles out there and I want things to fuse together, what needs to happen? It turns out you can't be too hot, because the way you build up heavy elements is through a chain reaction of nuclear reactions. So you say, oh, well, I'll take a proton and a neutron and I'll fuse them together and make deuterium. And then I'll take deuterium and another proton and fuse them together and I'll make helium-3. And then I'll take another deuterium in there and I'll get helium-4. And then I'll take 3 helium-4s and smash them together and get carbon. I've got this big chain reaction that's happening, right? Only the early universe works against you because things are hot. So you try to take that first step and say, oh, proton, neutron, deuterium, and now I want to form something else, but oh crap. 10 to the minus 17 seconds pass, and a photon comes in and it hits my nucleus. And what happens? A photon has so much energy that it splits them back apart. And you say, crap, well, I have to play this waiting game then. I have to wait until these photons from the early universe, these high energy, short wavelength photons, they have to redshift. They have to get cooler so that eventually I can form deuterium and not destroy it right away. So you say, okay, well, I'm going to do some math and I'm going to say, how much of all the different elements should I get depending on what's in my universe? So you work out the math and it turns out that, in the early stages of the universe, you can get about 75% hydrogen, 25% helium, about 0.1% leftover deuterium or helium-3, 0.01% maybe, and then 1 part in 10 to the 9, 1 part in a billion is lithium, and nothing else. And you look at that result, you look at what you get and say, geez, well, I measured the expansion rate of the universe and I knew all the combined stuff in it has to account for it. But when I look at how much matter do I have from these observations I made and the laws of nuclear physics and the framework of the Big Bang,
there's not enough.
Not only is there not enough, there's not enough by like a factor of 20. There's like got to be 20 times as much stuff as all the normal matter combined. So I say, okay, well, I have different ways of measuring the universe. So I can look at the cosmic web and I can look at how galaxies cluster and I can look at the leftover glow from the Big Bang and I can look at these light elements from the Big Bang and I can look at distant supernovae and other what we call standard candles, objects that we know how they work so that when we see them far away, you can just say, oh, it's like a 50-watt light bulb. I see that thing and it looks faint, but if I know it's a 50-watt light bulb, then when I measure how bright it is, I can know how far away it is. So that's another thing that we do. So we bring all this together, and that's where we say, you know, about 2/3 of the universe is some type of energy inherent to the fabric of space. That's what we call dark energy. And about 1/3 of the universe total is some form of matter. Mm-hmm. But if only 5% is normal matter, then the other 27, 28%, it has to be some other kind of matter that doesn't absorb light, emit light, or interact with the normal matter by smacking into it. So that's what dark matter is. So we don't know exactly what they are because it's not like we can directly detect them, but we can indirectly detect them. We can look at them and see their effects. Mm-hmm. And since we know how gravity works, and we know how cosmology works, and we know how the expanding universe works, we can be confident in a whole slew of different ways that dark matter and dark energy are real, but we don't know what they are. Inflation is a little different because inflation is basically saying, look, if you went and said, hey, you know, Big Bang genius, I'm going to take this universe that we have now and go back in the past, smaller, hotter, denser, smaller, hotter, denser, smaller, hotter, denser. Why stop? I'll just go all the way until everything's in a tiny little point, until everything's in a singularity, right? Where all of space and all of time and all the matter and all the energy is compressed down into a single point. That was originally what people thought to do, but it turns out if you make that extrapolation, the laws of physics actually predict you will see a whole bunch of things that we don't actually see in our universe. So this was a problem that people working on the Big Bang were aware of and were thinking of in the 1970s. And in the early 1980s, that's where the theory of inflation came about, because people were asking the question, look, you can either tell me, okay, look, somehow the universe at the hot Big Bang, at the start of the hot Big Bang, it was born this way and it had these properties and no one knows why. And that's the end of the story. And if you say that and you're a scientist, I'll say, okay, at least try.
That's giving up, isn't it?
Try. To me, it is. To me, it is, because in science, if you say, okay, look, we see things started off this way with these initial conditions, what we love to do is we love to look for a mechanism. We ask ourselves, what could have given rise to a system that starts off with this initial set of conditions, right? So this is basically saying, I want to supersede the Big Bang theory, right? Again, not the TV show, the theory. So if I want to supersede it, what do I have to do? I always say there are 3 things you have to do if you want to replace an old scientific theory. Thing 1 is everything that the old theory succeeds at, you have to reproduce those successes. If you're like, hey, I've got a theory and it does all this great stuff, and I'm like, well, I've got an alternative that doesn't do that great stuff, you tell me go home until you do, because that's correct, right? I can't come to the table with something unless I could say, hey, everything your theory does, my theory also does. So it has to first off not obviously be wrong, because if I can't do the things that the existing theory already does, I'm obviously wrong. The second thing you have to do is say, look, I tried to explain something that the old theory didn't explain. Can I do it? The answer better be yes, right? This is how Einstein got his start with general relativity. He said, Newton, you're great, you succeed at all these things, but you can't explain why the orbit of Mercury works the way it does. So for Einstein to get started, he had to come up with a theory that worked the same as Newton's theory, where Newton's theory succeeded, and in that one place where it failed, his theory had to succeed. So that's a second thing it has to do. You're saying, okay, look, for inflation to replace the Big Bang, it has to give you this hot, dense, uniform, expanding state, and it has to explain why the universe was born with the set of properties we see and not with the set of properties we'd predict without inflation. And then you have to do a third thing that is even more difficult. You have to make novel predictions that differ from the original theory's predictions that people can go out and measure and see, is the new theory right or is the old theory right? And so if you can do those three things, then you can advance science and you can have a theory that replaces the old one. And that's what inflation says, is that, you know, if you had a phase of the universe where it wasn't filled with matter or radiation, but instead just energy inherent to space itself, that's going to make space double in size and double in size and double again in size. And very quickly, in a tiny fraction of a second, you will go from a subatomic scale to something that's inflated to be larger than the size of the visible universe. And then when inflation comes to an end, all that field energy gets dumped into matter and radiation. And that's where the hot Big Bang gets started. But the big things that make it different from the hot Big Bang without inflation is you don't get up to an arbitrarily high temperature. There's a cutoff. You only get as hot as that field energy from inflation allows you to get. And it also predicts, because of quantum physics, that when you have this inflating space that expands very rapidly, these little tiny minuscule quantum fluctuations, they get stretched to all different scales across the universe. So we predict with inflation that the universe should have been born with little tiny imperfections somewhere like on the 1 part in 30,000 level, where some places are more dense than others and some places are less dense than others. And we can actually predict, based on the spectrum of fluctuations that inflation should give you, what type of cosmic web should we get out. And that, again, when you take all that information and you gather all the data and you compare it to what you predict, that's, again, how we know, oh, well, it makes sense if you have dark matter and dark energy and inflation. And if you take any of those ingredients out, the observations don't match up anymore.
Wow, that was a lot. And basically what I took from that is we can be confident that inflation is not superseding or it's not abolishing, so to speak, the Big Bang Theory. It's adding to it. Is that?
I would say that's fair. Basically, if you say, okay, according to the Big Bang, the universe came from this hot, dense state, that's still correct. But if you want to say, oh, the Big Bang implies we go all the way back to a singularity, and then the universe Hadoukens itself into existence. No, not to a singularity. That's too far, right? You made an assumption early on, right? Back in 1927, right? Lemaitre made this extrapolation and he called it the primeval atom, or the cosmic egg, that goes all the way back to like one thing where everything starts from. And that's not a good assumption. We thought it was for about 40 years. And then we started realizing, if things got arbitrarily hot and dense, and it didn't ever expand at these inflationary speeds, then you would expect to see a different temperature in that direction versus that direction. When I look to the limit of what I can see here and there, why are they equal to 99.997% in any two directions I pick if they've never had time to communicate to each other? But inflation will fix that for you by saying, oh, well, when things expanded like that, then the thing over here and the thing over here, they used to be connected in the past. So when you're saying, why are they the same? It's because they used to be the same. And the inflating space just drove them apart. So there are, I'll just say there are at least 4 separate independent tests of inflationary Big Bang versus no inflation in the Big Bang that have been conducted, that we've gotten results back. And inflation is 4 for 4, and the Big Bang without inflation is 0 for 4. So there are still people out there who are like, well, but we could do this other test, and I'm waiting on the results of this test before I say that I believe this. And
it sounds like we've settled it. It is like, it's inflation
like you might need to convince yourself, but I'm thoroughly convinced because either inflation happened or something that is hitherto indistinguishable from inflation, but somehow isn't inflation, happened. So at this point, I'm content to say, look, I can't tell you the particulars of every aspect of inflation that happened. But if you're saying like, well, what if inflation didn't happen? And I'm like, okay, well, now you're in like Wayne's World territory and are asking me about monkeys flying out of my butt. Like it might be this monkey theory alternative that you have, but I don't have supporting evidence for that. Whereas inflation has gone and met all 3 of these very high bar to hurdle criteria that we've set up.
All right. So I got a couple more science questions for you. You mentioned Einstein a little while ago, and that's a good transition into this question. Actually, a couple months ago, I had a conversation with a friend of mine, Devin. He goes by Leophilius, and he's a content creator.
I see him on Twitter.
Yeah. He's really smart kid. I mean, not kid. He's in his 20s, but really, promoting science.
That's a kid. I'm in my 40s.
Me too. So, but I had him on an episode of Secular Soapbox on Promethean Secular Frontier, and he tried, and in my opinion, succeeded to educate our lay audience on what time is. And he talked about sort of the different theories of time. And by the way, I have a link to that show for anyone who's watching in the description below, and also Leophilius's channel for anyone who's interested. I strongly recommend it. But he is also self-studied, and that was a different show. And so I figure I have an astrophysicist here. I'm basically going to ask you the same question I asked him. What is time?
All right. Well, I can give you the dumb answer, which is time is the rate at which things happen, right? Okay. But what I look at is there are 3 things that are related that you can't really talk about one without talking about the other 2, and those are space and time and the speed of light. And this is something that's really important because right now, when I'm here in my chair, stationary, right? As far as I'm concerned, I'm stationary. I know the Earth is moving through space and around the sun and blah, blah, blah. But from my point of view, I'm stationary. I'm not moving through space. And therefore, my motion through time is maximized. I am aging at the rate of 1 second per second. And that sounds like a tautology, but it's not. Because if I cloned myself and I had my clone move, like my clone was like, oh, crap, I'm going to go, and I'm going to go this way really fast. And I go this way really fast. And then my clone is like, oh, well, I better go back and see what Ethan number 1 is doing. And it comes back really fast. Guess what? That clone and me, we won't be the same age. We will not have aged the same amount because my clone will have moved through space some. And the more you move through space, the less you move through time. What compared to what? That's where the speed of light comes in. So when you have a light beam or a light ray or a light photon, and you say light is traveling through the universe, that photon doesn't experience time for itself. All of its motion is through space. So the closer you get to the speed of light, the more you're moving through space, the less you're moving through time. So conversely, at rest is the most you can move through time and the least you can move through space. And in motion is moving through space more, so I age less.
That's special relativity, isn't it?
That's the core of special relativity, is the faster you move through space, the less you move through time, and the faster you move through time, the less you have to be moving through space. And special relativity sets that relationship that says if you move at this speed relative to this reference frame, that you age this much and distances look contracted this much relative to someone in that other frame of reference.
Right. And this is proven with, they've done experiments with atomic clocks where they've had one on a moving, aircraft, I think, or maybe it was a spaceship, and one stationary on Earth, and then compared the results later, and their times were off because one was moving. And so this is not just something that's like an idea or I was about to say theory. It is a theory, but it is, it's confirmed. Like, we know this to be.
We know the equations are right, certainly. We absolutely know that these predictions are borne out, and incredibly precisely, too. For example, you talked about like, oh, well, we could do it with something in orbit and something here on Earth. They have two different atomic clocks that are separated by about a foot, where one is just a foot above the other. Wow. And they can measure the difference in clocks down to like 17 significant digits. And so you can just see these like attosecond differences between these two clocks. And part of it is gravitational. That's the general relativity part. General relativity, if you were like, what's general relativity? General relativity is special relativity plus gravity. Mm-hmm. Easiest definition, special relativity plus gravity. What's special relativity without gravity is special relativity. That's why it's special, because it's a special case of the more general relativity. So you say, okay, some of it is due to this difference in gravitational field, but some of it is also due to the fact that if I'm on Earth and I have a higher thing and a lower thing, and they both make circles around the Earth, then the one that's further away from the center of the Earth makes a bigger circle, and the one that's closer makes a smaller circle. So nice. It moves faster.
So when we talk about the beginning of the universe, we're always talking about it from the perspective of the universe already existing, and then the observations of what happens after it's already there. When I get into theological debates or philosophical conversations, it seems that that's insufficient for most people. They want to know why it's there in the first place. Is there any scientific way we could answer that question? Does the question even make sense?
Well, okay. So when you ask why is the universe this way, that's like a question of purpose. Mm-hmm. And I've never, as a scientist, been able to provide a satisfactory scientific answer to a question of why. But if you wanted to ask a question of how, like, well, maybe how did our universe come about?
Right.
That's something that, I would say scientifically, you can say, well, if our observable universe as we understand it began with the hot Big Bang, then what are the signs of, if I said inflation set up and gave rise to the hot Big Bang, I would say, what are the things I could look for that are signs of inflation? And I told you I know of 4, and we found them. So I would say inflation came before the hot Big Bang. But is that sufficient to say inflation came before the universe? Because we still have space, we still have time, we still have the laws of physics during inflation, and worst of all, we only have that tiny last fraction of a second of inflation before it ends that imprints itself on our observable universe. As time goes on, light that's presently beyond the limits of our observable universe will eventually reach our eyes. So we'll be able to see a little bit more of the universe than we can see right now, But once you go beyond a certain point, that's it. There's information that's not accessible to us. I'm going to just say, if you went and closed your eyes and drew an imaginary sphere around the universe and said, everything within this sphere, we will someday be able to access and get information from, and everything outside that sphere, we can't, that's correct. So the amount of information contained within the universe that we can access is finite. And that in itself is a huge philosophical, like, that means something. The amount of information contained within the universe that we can access is finite, which means there are inevitably going to be questions beyond a certain boundary, whether that's in time or in space, that we do not have information about.
And you mentioned philosophy, and that kind of goes into my next question, because oftentimes even the word universe is defined differently in philosophical terms than it is in cosmology. We in science, we define the universe as the observable matter, energy, space, and time that you were talking about. And I often feel like in philosophical discussions, when people use the word universe, they're talking about anything and everything that's ever existed at any time. And that's not exactly the same thing, is it?
I mean, I certainly don't think so, but philosophers use a vocabulary that physicists don't. For example, my favorite illustration of a difference between a philosopher and a physicist is if you ask them to define the word nothing.
Mm-hmm.
I honestly, the physical definition of nothing is
well. Before you answer that, Ethan, let me do this properly, because I anticipated that you might transition to that. So, okay, What is nothing? And the follow-on is, can something come from nothing? So, carry on.
Okay, so when you say nothing and you're a philosopher, you're thinking like, I'm imagining the pure essence of nothingness, where I take everything away. There's no space and no time and no laws of physics and no anything, and we're outside of it all. And this is true nothingness, the nothingness of empty, non-being, all of that. And I look at that and I say, well, that's great that you went and imagined something that isn't physical. But when I talk about physics or the physical universe, I really am only interested in the physical. I'm not interested in what I can imagine. I'm interested in what is real or what is true. And so this is much closer, ironically, maybe, to a Buddhist concept of nothingness, which is that nothingness is really like the emptiness of space, which contains the whole universe. So if I say I want to talk about physical nothingness, then what I'm going to do is I'll take it all away. I'll take everything that's a quantum of energy away. I will take every source of mass out of the universe, every source of electric charge, every atom, every molecule, every subatomic particle, every photon, every neutrino, every quantum of everything. I'll take it all away. I'll say, okay, I know in general relativity, the fabric of space-time is curved, so I'm going to push all that away and just have my space-time be flat. And it can still be expanding or contracting, but it's there. And then you start asking, well, what about the laws of physics? And I can't take those away. I cannot have nothingness without having space and time and the laws of physics. The laws of physics can be different. They can, because they are different at different energies in the universe. But I can't just get rid of them. It's not like they don't exist anymore. So if I say that's my definition of nothing, is empty space, but the laws of physics are still there, time still exists, and space still exists, then yeah, something can come from that. No problem. All you have to do is learn quantum physics. Quantum physics says, oh, well, guess what? Empty space isn't completely empty, because the quantum fields of nature they're present even if you don't have any particles. If I made this big box full of empty space and I was like, what's in here? Guess what? The electromagnetic field is still there, and the chromodynamic field is still there, and the gravitational field is still there, and all these different fields are still there. So, we've done experiments to prove that they're there. If I take two parallel conducting plates and I put them in a vacuum where there's nothing, what are they going to do? Will they just sit there? Will they only be attracted by the force of gravity over really long times? No. There's an electromagnetic force between them known as the Casimir effect, because outside of the plates, you can have every wavelength possible, but between the plates, you can only have the wavelengths that fit between these plates. So certain what we call modes, electromagnetic modes, are forbidden between the plate, which means there's less force between them and the plates will actually attract each other. And we did that experiment. It's named the Casimir effect because it was predicted by Casimir, I think back in the 40s. And then maybe 20, 30 years ago, this guy named Stephen Larmoreau went and did the experiment and measured it, and it's real. This is correct. So if you want to say, Ethan, we want to deal with a definition of nothing that is still physically consistent with the universe, then yes, something not only can come from nothing, but it inevitably will. If you're saying, I don't like your definition of nothing, then I don't know, because you can come up with the definition of nothing that has no physical meaning. And then if you ask, can something with physical meaning come from this thing with no physical meaning? I really can't tell you anything other than I don't know. That's beyond my scope.
Thank you for that. And really the purpose of that question was to kind of address some of the arguments that I hear in favor of supernatural causation and all these other things. But before I get to that, I might as well ask you, I already know the answer to this, but some of the audience may not. What are your religious views, if any?
Well, so I was raised, I guess, on the border between Judaism and atheism, but because I grew up in New York, you're around people of all different religions. Mm-hmm. Like some of your friends are Catholic and Protestant or Baptist or Muslim or Hindu or Buddhist, or, it's New York. So you get a hodgepodge of everything and everyone and their mother, and, people believe all sorts of things. So, mm-hmm. My religious views basically come down to, look, when I look at what happens in the universe, I try to explain it without resorting to invoking anything supernatural. Because if you can explain it naturally, then why would you add on this extraneous structure just to fit your own prejudices? That doesn't make sense to me. So I don't really go there. But if you want to say, hey, look, here's what we have as the universe, and you're telling me there's a fundamental limit to how much we can ever know about it. Do you think it's likely, unlikely, possible, impossible for all of what exists to have come about naturally through some chaotic process? Or was it deliberate? Did it come about because, I don't know, some higher dimensional being was messing around on their computer, making a simulation, and poof, this universe popped out and it's us, and that's a lot of things are possible to me. I haven't found any explanation that's been compelling to me in the way where I've listened to it and said, oh, yeah, that's got to be right. I've heard a lot of ones that have pinged me in the opposite direction, but I'm very open-minded about it. So if you say, Ethan, do you believe in God? Well, if God means I think it's plausible that the universe was created somehow as opposed to just came into existence, I think that's totally plausible. If you're saying I think this specific religion in this book and everything it says is correct and infallible, probably not so on board with that. But as soon as anyone becomes prejudiced or bigoted or a Nazi, I am the Jewiest Jew you'll ever meet. Because if you're going to go after one of us, you're going to go after all of us, and that includes me. There was a time when I was young where someone said to me, look, whether you believe in God or not, being Jewish is something else, because when the Nazis come after you, they're not going to ask, what do you believe? They're going to ask, what's your last name? Mm-hmm. What does your nose look like? They're going to ask these questions, and guess what? If they're going to kill you because they call you Jewish, say you're Jewish. So it's sort of this thing where, is it really fair to let people who are spouting hate define that for me? But I will. I happily will. I'll stand up with anyone who's being oppressed or threatened. And when I see those shirts that say 6MWE on them, if you don't know what that means, it stands for 6 million wasn't enough. I'm going to be the first one there opposing that.
And I say amen in the most secular sense of the word possible. With respect to, it sounded like you were offering an agnostic stance when it comes to the existence of gods, and you don't go to the supernatural, which is fair and something I would expect. With that in mind, I'm sure you've heard cosmological arguments proposed by William Lane Craig and various other people purporting that the universe had to have an intelligent designer, an intelligent creator. It's finely tuned. The Kalam cosmological argument is very popular. This idea that the universe had a beginning, anything that began. Wait, I'm screwing it up. Gosh, I'm drawing a blank. The universe, anything that begins to exist had a cause. The universe began to exist, therefore the universe had a cause. You would probably agree that the universe, in the cosmological sense, had a cause, and I think you just did a pretty good job of explaining inflation and all of that. But beyond that, beyond the point to where we can't see what started everything or where everything came from, do you think this is even a cosmological argument? I mean, are we talking cosmology at this point?
So when I was an undergrad, I took a philosophy course, and my professor was a guy named Derek Darby. And he's an interesting philosopher who his real focus is African-American philosophy and relations in the United States. And, when we went through some of the things, he brought up some older cosmological arguments for the existence of God. And as they've come up throughout history, he did one by Aquinas. He did one by that came out in the 60s. He did, and I started realizing, first off, all of these arguments that were made, we can look at them from a physics point of view now and say, this isn't even a correct cosmology. Like, you're making arguments for the existence of God because you are invested in the conclusion that, and therefore God exists.
My cat's very interested in this, by the way.
This is perfect catnip right here. If you arrive in an argument and you're saying, I already know what my conclusion's going to be, and I'm going to make an argument to try and justify this conclusion.
You've gone the wrong direction.
I'll just say, look, I'm 43 years old, and my patience for that type of reasoning is decades gone. I have none for it. So if you're saying, well, I'm coming at this from the perspective of I have a conclusion and I'm going to make up arguments along the way to justify what it is, then I know where you're coming from. And I'm just going to say, look, you've committed to this conclusion, not to the logic behind it. So if you didn't logic yourself into this position, you're never going to logic yourself out of it. That's not how it works. So when you say, okay, look, here's the thing. Would you say that the universe has a first cause? Would you say that? And I'd say, I can't say that. for two reasons. One, I told you I can only go back to the final little tiny fraction of a second of inflation. Certainly, almost certainly, more inflation occurred before that. How much? I don't know, because we have no constraints. Did inflation go on forever? Maybe. You could say, well, we've got a theorem. We've got the Borde-Guth-Vilenkin theorem, and that says that the universe in an inflationary state is past time-like incomplete. And I'm like, okay, well, do you know what that means? And you say no, because you're being honest. And I'll say, okay, well, all that means is if I take any 2 points in the universe and I say go back in time in an inflationary universe, they'll eventually get asymptotically close to each other. Right? You remember what an asymptote is from math? They approach.
No, I was just about to ask you.
They never meet, but they get arbitrarily close. So every point will do that in an inflating space-time. They'll get arbitrarily close together. Well, guess what? That doesn't actually tell you anything. It's possible that this inflationary state was eternal to the past. It's possible that some non-inflationary state existed before and had the right conditions to give rise to inflation. But I can't say for certain that the universe had an ultimate beginning, that time, you have a moment where time began to exist. I can't say before that, but maybe outside of that. But the second thing is, I already told you about quantum physics. I already told you that things happen, effects happen without a cause all the time. So if you are playing this logic game based on your intuition and not the logic that the universe actually obeys, what game are we playing here? You're trying to logic yourself into a position where you know you're using incorrect classical non-quantum logic. This is not how the universe works. Why would you make this argument?
I'm not sure that they do know that, in fairness. I'm not sure that they know that. I agree with your conclusion that the methodology is wrong, but I think people making the arguments haven't really thought it through to that extent. But
well, I think William Lane Craig knows, and I think he's being disingenuous.
Really?
I mean, maybe I'm giving him too much credit for thinking that he knows what he's doing, but surely, given all the people he's debated, this has been explained to him.
Yeah, he's never changed.
Chooses to ignore it
on this at all, despite all of the debunking. I mean, I've even not officially, not anywhere, but I can see right through his argument, and I've tried to debate his model many times with people. And it seems really easy to get given the evidence, just even at my level. But it's a
3-step argument, and the first 2 steps are unsubstantiated. I won't say they're wrong. I'll just say they're unsubstantiated. You can't say the universe exists, therefore it has a cause. No, that's not consistent. You also can't say anything that exists had a creator. Well, why? Why would you say that? Is the alternative so unpalatable to you that you can't even consider it? Because I can consider all sorts of things that aren't true. I just considered philosophical nothingness and told you, well, it's not physical. I can consider it. I can imagine it. And then what do we do with it? Well, nothing, because it's not physical. But at least we can consider it. Can you not even consider that something could have been eternal? That something could have always existed?
They can. Unfortunately, it's God. And so that doesn't really get us anywhere, because that's just question begging again. But in the few minutes that we have left, I got 2 more questions for you, and then kind of a non-sciencey, just sort of fun question. But
let's do it.
These words, hypothesis and theory. Theory is a word that has all sorts of usages, and people like to shoot down theories because that's just a theory. And, evolution's only a theory, and Big Bang, that's just a theory. What is a hypothesis and what is a theory? Just let's get that out of the way for the audience, and then we can move on. How would you define scientific theory, and how does it differ from a hypothesis?
Okay, so when we say scientific theory, I assume that we're talking about an accepted validated, confirmed, and thoroughly tested scientific theory. I assume we're talking about a consensus theory like the ones you mentioned, like evolution, like the Big Bang, where the overwhelming majority of professionals working in the field accept this as their starting point that everyone agrees on for the next scientific steps we're going to take. A scientific theory is basically, it's two things. It's like the sum total of all the facts and all the evidence that we've accumulated in the context of, well, here are the laws that are established, here are the ideas that are established, here are how the puzzle pieces fit together, and here is this framework we have for making sense of the universe. We can make predictions, we can make postdictions, we have a range of validity that it works for, and outside or beyond that, it may or may not work to various approximations. But that's what a scientific theory is. And this is very different from the colloquial definition of theory, where you're talking about like, oh, like this is, I have a theory that the moon is made of cookies and cheese, and I could fly there in a rocket ship and eat it, and then there won't be any moon at night because I was hungry. And that's, you know, first off, you can call that a theory, but that's not a scientific theory. That's I won't even call it a hypothesis. It's an
I was gonna
idea.
say
that's an idea.
Because that's there's like something you just came up with no evidence for it.
Yeah.
That's not even, I don't even know if that's falsifiable. Well, it is. You just go there and you take a bite out of it to see if it is, but.
Right. So a hypothesis is more like a theory that's incubating. It's a theory that has, it's like that colloquial use of theory or idea that maybe hasn't been advanced to the point where we can say it's a scientific theory. But scientific theory, like when you say, is evolution a scientific theory? Yes. Is it our best scientific theory? Well, we've got a lot past Darwinian evolution. Like Darwinian evolution is still true over its range of validity, but Darwinian evolution occurs because of genetic information getting passed down from one generation to another. So the science of genetics has built upon evolution, and DNA has built upon genetics. And so we talk about like, okay, look, not only is evolution true and a correct, valid scientific theory, but science at this point is a good 150 years past it, where we've built upon it. If you want to go back and challenge, basically, in my mind, what's already Dark Ages science, like this is science that my grandfather's grandfather, you know, could have learned if he was interested in science. Like I don't really know why you would reject this. It's sort of like in my field, I explained dark energy to you. Dark energy, you know, people started talking about it in the early 90s. There was some really good evidence that wound up giving a couple of teams a Nobel Prize. The evidence came out in 98. I entered grad school in 2001. Everyone in the field had already accepted dark energy, and I was slow, right? Because I was like, well, what about this objection and this objection and this and this and this and this? And
you were one of those.
I was, but also I learned, right? I was like, well, what is the evidence and what are the objections and how well do they hold up? And you know, the community did a great job of ruling out all of those objections. And by 04, 05, I had no legs to stand on. There were still people in the field who try to poke holes in dark energy, but these are not good arguments. And, you know,
they're outliers,
they're very easy to shoot down, right? This is a fringe scientist operating outside of the consensus, and it's important to challenge the consensus, but it's important to challenge it intelligently, not stupidly, right? You don't want to challenge it because you're making mistakes along the way, and that's the only way you can pose a challenge to it. I feel like a lot of the people who, you find yourself arguing with are not coming at this from a scientific point of view at all. They're coming about it, like I said earlier, from an ideological point of view where they've decided what the conclusion has to be, and they're going to get there, damn it, by hook or by crook. So,
Well, you are definitely coming from the scientific perspective. And speaking of challenging the consensus, the previous question had to do with what is a scientific theory. I often hear about string theory. Mm-hmm. And I think I read an article recently. I think it may have been written by you.
I write things.
I read a couple of articles on string theory, and about both of them imply that this is something of a misnomer. So is string theory actually a scientific theory?
No. That's the quick answer. The quick answer is no. It does not meet the criteria of a scientific theory.
Why are we calling it that?
Well, there are other definitions of theory, including in mathematics. You can have a mathematical theory that obeys a certain set of rules and axioms and self-consistency relations, and string theory is a mathematical theory in that sense. But to be a physical theory, I told you, you have to say, okay, I'm going to reproduce all the successes of the existing theory. And what is string theory? Well, string theory is a 10-dimensional theory that gives you brand-sticky gravity and a whole bunch of unifications and supersymmetries that we don't see in nature. We only have 4 dimensions, not 10. We only see the tensor part of gravity, no evidence for the scalar part. We only see the standard model particles. We don't see any supersymmetric particles. We don't see any evidence for these extra dimensions. We don't see any evidence for super Yang-Mills field or.
And that's not to say that none of this exists, or that
it's not to say it doesn't exist, but it is to say, if these things exist, we have to at least find one of them to say string theory does some things successfully that the current theories don't. Because as it is, string theory just gives you a bunch of, stuff that doesn't appear to exist. And that's not interesting enough for me to work on. I don't worry about people who do think it's interesting to work on, because do what you're interested in. I'm not going to tell anyone else what to find interesting and what to work on, but I am going to say always, when you're talking science, you've got to confront your predictions with reality. If you don't have any predictions that can be measured, you better get to developing your technology so you can measure them. Otherwise, you don't have a testable theory.
I lied because speak of the devil, he showed up. We were just talking about him earlier. So Leophilius, who's watching, wanted to ask whether you think time is a physical property of reality or an abstraction of the human mind. We kind of touched on it a little bit, but from the perspective of this question, is time actually a thing, or is it?
So I'm someone who believes that if a tree falls in the forest and no one is there to hear it fall, it goes and it still makes a sound, even if no one's there to hear it. That isn't to say that we live in an observer-independent reality. I think that quantum mechanics has shown us the observer may play a role at the very least. But I think time is real. I think time is real. It's physical. I think space is real. I think it's a physical part of reality. And I think we're moving through it. People worry about, is time a human construct? And I'll tell you, my animals appear to age just as much as I do. All the non-human things I interact with, the Earth had no problem aging 4.5 billion years before I was born. The universe had no problem aging 13.8 billion years before humans ever arose. And I don't think there's any compelling reason to think that time only came into existence with the existence of humans and will cease to exist when humans cease to exist. I think time is quite physical and we can measure it, and it's hard to get more physical than that.
All right, this will be the last question we take from the chat. Can a supernova in one solar system affect a neighboring solar system's planets in any measurable way? I'm not sure how neighboring he's imagining, but
I mean, that's pretty much the answer. Is if you're close enough, yup, and if you're far enough away, then nope. So if you're worried about Betelgeuse going supernova, no, we're fine. We're enough hundreds of light years away that we're fine.
What about Proxima Centauri?
If Proxima Centauri somehow, grew to 1,000 times its current mass and went supernova, I would say in that situation, if it was a supernova that resulted in collimated jets and one of those jets happened to point right at us, it could potentially sterilize life on half the planet, the half that it happened to strike. So we're talking about large amounts of energy getting deposited in very short periods of time. It is possible for a supernova, if it's close enough, to cause, at the very least, a great mass extinction event.
All right. And then my final question.
All right.
Have you ever met Neil deGrasse Tyson?
I have. Do I have to answer this? No. Neil deGrasse Tyson and I have crossed paths a couple of times. And
did you get into fisticuffs?
The couple of times we have crossed paths, he has treated me as though he does not know who I am. And he may know who I am, or he may not know who I am. But that has been my personal experience with Neil deGrasse Tyson.
Okay. Do you think that is on purpose, or could he just be could it be innocent, or is it or do you even care to speculate beyond that?
I feel charitable today, so I'm gonna say I look forward to the opportunity to meet him in a situation where he feels comfortable enough to say hello and be cordial to me. So if that situation arises, I look forward to the opportunity.
Tell us about what you've got coming up.
Big things coming up and happening right now. You announced me as being at Forbes, where I have been for 6 years, but just yesterday I started a new job at Big Think. So I will have a new online home at Big Think. Later this year, we will be starting a Kickstarter or Indiegogo to bring an Encyclopedia Cosmologica to life, where on every page, we're going to step through the history of the universe in 100 million year chunks. And I've got a great collaboration going with a designer and a layout artist, Will Lidwell, and two awesome space artists, Mark Garlick, who's based in the UK, and John Lomberg, who was Carl Sagan's premier artist for Cosmos. So I'm really looking forward to that project, Encyclopedia Cosmologica, coming late 2020.
Ethan Siegel, thank you so much for joining me today. This was quite informative. I had a great time. I'm glad Leophilius was able to stop in because we kind of talked him up. But definitely on my list is Cosmology. Uh-oh. Somebody was upset.
You have that. Cats, I have dogs. There we go.
These
they had to make an appearance before I left.
I really appreciate you coming on. Hopefully I can get you sometime in the future when I think of maybe, I don't know, maybe I'll talk about, have you talk about black holes and wormholes, because we didn't get to that. And I'm sure we can do a whole episode revolving around that, combined with our mutual interest in Star Trek. But this was a blast. I hope that everyone watching got to know the universe as you know it, or at least half as much as you know it. We have social media links to Ethan down below in the comments, at least to Forbes, and also your blog. Are you still doing that, by the way?
Starts with a bang, 5 days a week, pretty much every week since 2008. So we're still going strong. You can still find my legacy content on Forbes and new stuff at Big Think, at Medium, and on my Patreon. So check out. I'm Starts with a Bang at all of them.
There you go, guys. If you've enjoyed this show, Please hit the like button and subscribe to Tang, the Atheist Network group, for more awesome secular content. I will be off next week, but I shall return on the 28th with another great episode. And join me in the Discord as well. Ethan actually is working tonight and has still got some stuff to finish up, still doing some sciencey things behind the scenes. So he will not be able to join us in the Discord, but maybe some of the questions that come up in the Discord we can follow up on in a future appearance if you're willing. So
sounds like a good plan.
Awesome. So for the rest of you guys in the chat, join me on Discord. And for Oz, producer Wes, Sunny Shell, my name is Brycearonee. Have a good morning, a good afternoon, and a good night. I'll see you next time on The Bryce is Right.